You're all familiar with the Big Bang, the colossal explosion that marked the beginning of time and space. But what if the birth of our universe was even more extraordinary than we've come to believe? Imagine, for a moment, a universe not birthed from an explosion but from a white hole. This concept, though purely theoretical and speculative, presents a fascinating twist in our cosmic narrative. A white hole is the exact opposite of a black hole. While a black hole is like a cosmic vacuum, swallowing everything in its vicinity, a white hole is a cosmic fountain, spewing out matter and light. White holes emerge from Einstein's equations in general relativity, similar to black holes, but with a critical difference. A black hole has an event horizon from which nothing can escape, whereas a white hole has an event horizon from which nothing can enter, everything can only emerge from it. Inside, there is an enormous tunnel-like structure that, instead of stretching indefinitely, contracts and eventually opens up. This phenomenon is predicted by Einstein's equations. According to general relativity, the gravitational collapse of a massive star leads to the formation of a black hole, a region in space where the gravitational pull is so intense that nothing, not even light, can escape. The boundary of this region is known as the event horizon. White holes, on the other hand, are essentially time-reversed black holes. Instead of capturing everything that comes near them, they are predicted to expel matter and energy, acting as sources rather than sinks in the cosmic fabric. Physicist Carlo Rovelli proposes that a black hole could transform into a white hole, provided it meets a key condition: it must be exceptionally small. This presents a significant challenge since most black holes we observe in the universe are massive, making such a transformation highly improbable. However, Rovelli adds an interesting dimension by suggesting the possibility of a quantum jump, adding a new layer of complexity to the theory. By incorporating quantum gravity into calculations, scientists realized that quantum jumps could occur with a certain probability. If a black hole is large, the probability of such a transformation is negligible. However, black holes evaporate over time, emitting energy and shrinking in size. If a black hole becomes small enough, the probability of it transforming into a white hole increases significantly. Eventually, it becomes almost certain. Astrophysically, the likely scenario is that any black hole will take an incredibly long time, billions of years, to shrink. The time required for a black hole to become small enough for this transition, as computed by Stephen Hawking, is much longer than the current age of the universe. However, inside the black hole, time behaves differently. While billions of years pass outside, only seconds or minutes pass for an observer inside. The transformation into a white hole, once initiated, would be nearly instantaneous from an internal perspective. The concept of white holes is intriguing but remains highly theoretical. They have never been observed, and their existence poses significant challenges to our understanding of physics, particularly regarding entropy and the arrow of time. However, this has not stopped theorists from speculating about their role in the cosmos. If Rovelli's ideas are correct, they could help resolve long-standing black hole paradoxes. Stephen Hawking initially proposed that any information entering a black hole would be lost forever, as the singularity at its center marks the end of time. However, Hawking later explored how black holes radiate energy and eventually disappear. This led to the famous information paradox: does the information that enters a black hole vanish, or is it somehow preserved? If information were truly lost, it would break the fundamental principle of determinism in physics, which states that information cannot be created or destroyed. Recent research suggests that information is not destroyed but is somehow encoded in the radiation emitted by the black hole. However, the exact interpretation of this remains debated. Some theories propose wormholes linking the black hole's interior to the distant universe, while others suggest the holographic principle, where all information about the interior is stored on the event horizon itself. These advanced ideas have significantly shaped modern discussions on black hole physics and quantum mechanics. This principle, while primarily concerning black holes, opens up intriguing possibilities regarding the birth of our universe. If information is preserved within black holes, could a similar process have played a role in the emergence of our universe from a white hole? This idea challenges the traditional view of the Big Bang as a singularity and instead suggests a more complex origin. Rovelli's theories on black and white holes, combined with insights from the information paradox and the holographic principle, offer a fresh perspective on the birth and evolution of the universe. However, while these ideas are grounded in theoretical physics and have garnered significant interest, they remain speculative and are the subject of ongoing research and debate. The first indirect evidence of black holes emerged in the 1970s when astronomers observed stars orbiting invisible objects, suggesting the presence of an unseen massive companion. However, it wasn't until much later that black holes were widely accepted as real astrophysical entities. Similarly, the concept of white holes may one day transition from pure speculation to observable reality.